Hello friends, we'll learn today velocity and acceleration diagram. So, example is taken. This is space diagram drawn with scale 1 centimeter equal to 100 mm. I will explain this space diagram first. Link AO is fixed. AB is a crank rotating in a counterclockwise with RPM 120. Link OC is an oscillating arm. B dash is a point on link OC. CD is another link and D is a slider here. While solving the velocity acceleration diagram problem, first of all we have to calculate the angular velocity omega for the link whose RPM is given. In this case, RPM of link AB is given. It is 120 RPM. Therefore, we can calculate omega AB for link AB. That we know the formula omega AB equal to 2 pi n AB divided by 60. If you put n AB equal to 120, you will get 12.57 radian per second. After calculating omega, you have to calculate velocity of that same link. That is in this case link AB, velocity of link AB. We know the formula for velocity VAB equal to length of link, that is AB, into omega AB. If you put value of AB is given here it is 150 mm. We have to convert this in meter, 0.15 into omega AB, that we have calculated 12.57. If you calculate this, you will get with the calculator 0.19 meter per second. After calculating this velocity, we will move towards velocity diagram. There are some steps to draw a velocity diagram. While drawing the velocity diagram, first of all, you have to take a point anywhere and you have to take all the fixed points from the mechanism to that point. Okay, here in this case from the space diagram it is clear that point A and point O are fixed, and for velocity diagram we will use notations small letters. That is here A, for capital A we will write small a, and for capital O we will write small o. Then we will start with the crank AB. For crank AB, it is rotating in a counterclockwise direction. Its velocity will be perpendicular to this AB, as link AB we know for link AB, let this is the link AB and it is rotating in a counterclockwise direction. Then velocity vector of link AB is perpendicular to AB and towards the direction of angular rotation, that is in this direction. And for this vector we have calculated magnitude 0.19 meter per second, and now we have the direction, that is in this direction. Therefore we can draw a first vector with suitable scale and in the left direction, that is in this direction. For this purpose I will take a scale 1 centimeter equal to, sorry, here calculation is 1.9 meter per second. I will take here scale 1 centimeter equal to 0.19 meter per second. Therefore 1.9 meter per second will be equal to 10 centimeter. So first vector will be of 10 centimeter and will be perpendicular to this link AB. We can draw a length, we can draw a vector perpendicular to this and will pass. So we can draw this first vector with a 10 centimeter and perpendicular to AB and passing through the fixed point. We'll name this point small b. The arrow will be in this direction. After drawing a vector AB, we have to move towards point B dash. We have to move towards point B dash. And while moving from B to B dash, we have to draw a vector for a slider. This slider is sliding on a link OC. Therefore, its velocity vector will be parallel to its sliding path, and its sliding path is this link OC, and we have to draw a vector parallel to this link and passing through the B point. Therefore, we have to draw a vector parallel to this and passing through point B. Here in this case we don't know the magnitude for this B dash, but we know the direction only, that is parallel. So we can draw in this direction as well as we can draw in the opposite direction, that is in both direction. This is only locus of B dash, and we know the point B dash, will lie on this locus, that is here as well as here on this total locus. Okay, so after drawing this locus, we will move towards fixed point. We started with a small a and we have drawn this much vectors. Then we will move with small o. After point O, point B dash is there, O to B dash, and we can draw a velocity vector for OB dash, and we know the velocity vector is always perpendicular to this. So we can draw a vector perpendicular to OB dash, that is for this. Okay, so we can draw a vector perpendicular to OC and passing through the fixed point. As we know, this is the locus, this total line is the locus for B dash, so point passing through this and perpendicular to OB dash will intersect this locus, this one at this point, and we will get this intersection as a B dash point. Okay. After B dash point, on the same link C point is there, and we know O point is there for mechanism. Then after O there is a B dash, and after B dash there is a C. Similarly, in the velocity diagram, O point is there, small b dash is there, and small b will lie in the or next to the B dash point. So we know, so we want a distance B dash C. So to calculate a distance, for calculating distance B dash C, we have to write interpolation. We want a distance B dash C, and we know the distance of O B dash. Therefore, we have to write O B dash here. Whatever we have written for this ratio, just we have to write capital of this, that is B dash C and O B dash. And now we have to put the values. Small OB dash distance, we can measure it directly from the velocity diagram. We can measure it here. It is 8.4 centimeter. B dash C upon 8.4 centimeter equal to capital B dash C. Capital B dash C means from the space diagram, this distance B dash C, it is 2 centimeter, and scale is 1 centimeter equal to 100 mm, that is 2 centimeter equal to 200 mm, and we have to write it in a meter, or you can write both the dimensions in mm. And next one is OB dash, that also we can measure from the space diagram. OB dash, it is 5 centimeter, and with converting with the scale, 1 centimeter equal to 100 mm, 5 centimeter equal to 500 mm, and we'll get, after calculating this B dash C distance, it will come 3.36 centimeter. So after getting this distance 3.36 centimeter, we can take distance 3.3 centimeter in a scale, and we'll get a point C on the same line extended to this B dash. Okay, this is B dash. After B dash, C point will be there at a 3.3 centimeter. Just we have to draw this line at 3.3 centimeter. That is, here it is only 3.3. Okay, so this is small c. So now we have point A, B, B dash, C and O. For a link CD, okay, the same link CD, we have to draw a velocity vector perpendicular to this CD. Okay, so just we have to draw a perpendicular to this and passing through the C point. Okay, we have to draw locus of this. I will draw this with pencil. And now this is the locus for D point, but we don't know D will lie on this side or on this opposite side. But point D is a slider, therefore we can draw a velocity vector for a slider. We know velocity vector for a slider is a parallel to the sliding path. Okay, this is this horizontal line. Okay, this horizontal line is a path of sliding. We have to draw a vector parallel to this one and passing through the fixed point, okay, to get a point D. And now initially we have drawn a vector for a D, so its intersection will be point D. Okay, so here it is the intersection for the initial locus. So you can draw this one. So this point is small d. So in this way we have completed our velocity diagram. After completing this velocity diagram, we have to make just chart like this. Okay, you can pause the video and you can write down this chart. I will explain this chart. Serial number, link, then calculations. Okay, calculation with the help of scale, and the last one is a velocity. Okay, first link is here, it is a AB, and for AB velocity vector is vector AB, that is this vector AB, and here it is 10 centimeter, that is AB into scale, 10 centimeter into scale, 0.19, it is 1.9 meter per second. Actually this one we have calculated in our calculation, VAB equal to 1.9 meter per second. But the same method we have to follow. We have to just measure the distance from the velocity diagram. We have to multiply it with the scale. Here it is 0.19. So for B dash, that is this vector, here it is 5.5 centimeter into 0.19. So 1.045 meter per second. For OB dash, that is this one, it is 8.4 centimeter into 0.19, 1.596 meter per second. Okay, the interpolation calculation, that when drawing this one I have done a rough one, but while drawing the or while preparing the chart, you can make this calculation in a chart. B dash C interpolation, B dash C 8.5, B dash C upon 8.4 equal to 0.2 by 0.5. It will give 3.3 3.36 centimeter. As this distance is b dash c is a 3.36 centimeter, you can multiply it with the scale, so you will get velocity of vector of b dash c. It is 0.6384 meter per second. Similarly for OC, that is just total OC, for link OC, this one 2.9 into 0.19, so 0.55 meter per second. For slider, it is important one. In question mostly the velocity of slider is asked. Just you have to measure this one, OD. This is velocity vector for a slider. This distance, here it is 11.4 centimeter into distance 0.19 equal to 2.16 meter per second. After completing this velocity chart, you have to prepare a chart for acceleration diagram. I have prepared this chart for acceleration diagram. Here columns are like this: serial number, then link, accelerations, calculation, and direction for acceleration vector. For first link AB, while drawing the acceleration diagram, you must know the basic for acceleration diagram. Whenever mechanism is in a rotary motion, or one crank is there and some links are having oscillating motions, then for each link there are two components. Here consider link AB, our initial link. There are two components for this link. First one is a radial component and second one is a tangential component, that is radial acceleration and tangential acceleration. Radial acceleration, its magnitude is always v square upon the length of link. V square upon length of link. And tangential acceleration is length of link into angular acceleration. Alpha is a angular acceleration of that respective link. And direction for radial acceleration is always parallel to that link and towards the center. And for tangential acceleration, it is always perpendicular. That basic information is required while drawing the acceleration diagram. I have prepared this acceleration chart already. Okay, I will explain this chart. Serial number, link, then accelerations, calculations, and directions. First one, link AB. As we know, for each link there are two components, radial as well as tangential. And for radial acceleration, it is velocity of AB square upon length of link. Here it is AB. VAB, that we can take from the velocity chart. This velocity chart, AB velocity is 1.9 meter per second. Therefore, here I have taken 1.9 meter per second, and AB, that we know 150 mm, that is 0.15 meter. For this calculation, we will take each dimensions in meter and velocity in meter per second, so that we will get acceleration in meter per second square. And for first link AB, we will get radial component 24.06 meter per second. And direction for this radial acceleration is parallel to AB and towards A. For next link B dash, here slider B, but this slider is in two motions. This slider, here in this case slider B is having rotary motion about point A and sliding motion about point, or sliding motion on link OC. Therefore, there are two components, one is a coriolis component and one is a linear acceleration. For coriolis component, direction is perpendicular to OC. Coriolis is always perpendicular to OC, and towards left or right, or towards which direction, that I will explain while drawing. But for magnitude, Coriolis component magnitude is 2v omega. Okay, 2 into velocity vector b b dash. Okay, the same one, v b dash, velocity b b dash. From the velocity vector we can find this one, b b dash. Okay, that we have calculated in a velocity chart. B b dash, it is 1.045 meter per second. So here taken it from the velocity chart. And omega OC, okay, angular velocity of the link on which slider is sliding. Slider is sliding on link OC, here OC. On this link, this slider is sliding. Therefore, angular velocity of OC is taken, omega OC. And omega OC we can calculate the same simple formula. Omega OC is equal to velocity of OC upon OC. Velocity OC can be taken from the velocity chart. OC, it is equal to 2.185 upon OC distance. OC is given here in the given data. OC 700 mm, or you can measure this distance OC, okay, 700 mm. Therefore 2.185 upon 700 mm, that is 0.7 meter. This will be 3.15 radian per second. Okay, that you have to put in the acceleration chart, 2v omega. So you will get acceleration 6.583 and direction is perpendicular to OC. And towards left or right, I will explain this one during or while drawing the acceleration diagram. Then linear acceleration, we don't know its magnitude, we just know the direction, it is parallel to the OC. Here OC is the sliding path, therefore parallel to the OC. Next link is OB, that is this one, OB. For link OB, two components, radial, tangential. Radial component, velocity square upon length, 1.596 upon 0.5. That 1.596 we can take from the velocity chart. Okay, OB, 1.596 from the velocity chart upon 0.5 OB distance. We can measure this OB distance directly. OB, here it is 5 centimeter, therefore 500 mm, 0.5 meter equal to this one, and its direction is parallel to OB and towards O. Towards O, why towards O? Because we are reading this link OB. We are reading this link OB, therefore towards O, first point. Always we are taking first point, and this reading is important because of this direction. For link CD, we are reading the same calculation for radial acceleration and tangential acceleration, velocity square by CD, CD, then we will get this one, but direction parallel to CD, as radial acceleration parallel to CD, no doubt, but towards C or D, towards C, yes, because C is here first point, CD, we are reading this link CD, therefore towards C. And tangential acceleration is perpendicular to CD. And the last one, acceleration of slider D. Actually, linear acceleration for slider, we don't know its calculation, but we know the direction, it is parallel to the sliding path. Here D is a slider, its sliding path is a horizontal line, its acceleration will be horizontal line. This is acceleration chart. Okay, we'll start drawing the acceleration diagram. And for acceleration, while drawing the acceleration diagram, some steps are there. First of all, we have to take the fixed points together, and for drawing the acceleration diagram, we'll use notations, small letters and with dash. Here fixed points are A and O. Okay, we'll take A dash and O dash, small a dash, small o dash. And we know the first link here it is AB. We'll start with AB, and from the acceleration chart we have the two vectors. First one radial and second one is a tangential. Here tangential acceleration is given 0. Here tangential acceleration is 0 because angular velocity is uniform. As omega is uniform, angular acceleration is 0. Therefore tangential acceleration AT is 0. So only one acceleration will be there parallel to AB and towards A. So first vector is parallel to AB and towards A. Before drawing this vector, we must know the scale for this. We'll take scale for acceleration diagram. Scale 1 centimeter equal to 2.406 meter per second square. Okay, in this acceleration chart, unit is meter per second square. You can correct this one. We can draw first acceleration vector, radial component of link AB. Okay, it is parallel to AB, this one, and its magnitude is okay like this, parallel to AB and passing through the fixed point, and as per the scale so the first vector here, this one, will get a point P dash. This is 10 centimeter. After finishing this vector, first vector, okay, we have drawn this in the downward direction because direction is here, it is towards A, that is in this direction, towards downward direction. Therefore fixed point to towards downward direction, this one. So we will get a point B dash. After this serial number 2, B dash. First one is a coriolis component. Okay, magnitude is known and it is perpendicular to OC and towards left. So coriolis component and its direction, just we have to draw a vector on the vector near to this diagram. From the velocity vector B dash, it is a sliding velocity for the slider B. We have to draw a vector parallel to this B dash near to this, like this. Okay, this one B dash. I am reading this B dash, therefore drawing B to B dash, B to B dash. This direction is important, B dash, and rotate this vector through 90 degree in the same direction as our crank is rotating, that is in counterclockwise 90 degree. So rotate this with counterclockwise, rotate counterclockwise 90 degree. B dash. So from this we can understand this is in the left direction. So B dash to the coriolis component will be in this direction. Okay, in this direction, and perpendicular to, as it is given in the acceleration chart, perpendicular to OC. There we have to draw a vector perpendicular to OC, this link, perpendicular to this and towards this direction from the coriolis component direction, and magnitude and with the suitable scale, converting this meter per second square 6.5. This point which we obtained is B dash, B double dash, and from this point next vector is linear acceleration. It is parallel to OC. We have to draw a line parallel to OC and passing through this point. Okay, here just we have to draw locus, so I am here drawing with pencil. Okay, in both direction, upward and downward, total one. Then move towards fixed points. Start with next point. Initially we started with A dash, then now start with O dash point. Okay, here OB link is there. Radial acceleration, it is 5.94 parallel to OB and towards O, that is towards O and parallel to OB. So we have to draw a vector parallel to OB and towards O point, that is in this direction. O is in downward direction, therefore we have to draw a vector. Okay, these vectors we are drawing with the dotted lines. Okay, we know its magnitude and direction. So 5.094 converted with suitable scale. So you will get a point O dash B double dash. So next one is a tangential component for OB. It is perpendicular to OB. Therefore you have to draw a vector perpendicular to OB like this. Okay, this one perpendicular, draw like this, and now this will intersect our initial locus which we have drawn after coriolis component, that is this locus. This will intersect here. So here this point is B double dash point. So now you can join this one. Now you can join point B dash B double dash with the continuous lines. Also you can join these two lines. So we have reached up to B dash point. We know from the space diagram O B dash C is a continuous one. Therefore for acceleration O dash B double dash and C dash point will be next to B double dash line. And for calculating the distance B double dash C dash, we have to take interpolation. We want the distance B double dash C dash, and we know the distance O dash B double dash, and just write capital of this. Okay, O dash B double dash, this distance we can measure with the help of scale. This is 3.8, and B dash C dash OB dash, that we can measure from the space diagram. So you will get distance B double dash C dash equal to 1.5 centimeter. So you have to just extend this O dash B double dash with 1.5 centimeter, and you will get a point C dash here. After C dash, link CD. For link CD, you have to draw two components, radial and tangential. Radial one is 1.5, 1 2. You can convert this with scale, and it is parallel to CD and towards C. Therefore draw a vector parallel to CD and towards C. Therefore like this and towards this direction, this one, this point will be C dash D dash. This is C dash D dash, and you have to draw a vector perpendicular to CD, like this, to get a locus for D point. I will draw this locus with pencil. I have drawn this one with pencil, and on for slider D, we can draw, okay, from this acceleration chart, slider D parallel to the sliding path and passing through the fixed point. Therefore parallel to the sliding path and passing through the fixed point to get a point D dash, like this. This will give intersection to the locus which we have drawn for D dash. This is our point D dash. After getting this, whatever we have drawn with the pencil, you can just join C dash D dash. So now our acceleration diagram is over. We have obtained all points A dash, B dash, B double dash, C dash, D dash. All points are over. This our acceleration diagram is over. Now you can measure acceleration of any link for the mechanism, and you can convert it with the scale. For example, if you want to measure acceleration of a slider, you can measure this O dash D distance. It is 4 centimeter here. Here it is 4.2 centimeter. Therefore, acceleration of a slider equal to 4.2 into scale, that is 2.406. You can calculate this to get acceleration of slider in meter per second square. Similarly, for each link you can calculate the acceleration. Here we are finishing this problem. Thank you for watching. If you like this video, you can subscribe my channel. Thank you.